Welcome to Electromagnetic Waves. In 1820, Ørsted published a very important paper. It was about how a compass needle can be deflected from magnetic north when in the presence of an electric current. This paper is often referred to as the birth of electromagnetism. Faraday investigated these effects, and in 1832 he published work on electromagnetic induction. In the late 1840s, Fizeau was doing his own experiments into the speed of light. He was shining a beam of light through a one-way mirror and across a very large distance of approximately 8,000 meters, where it was hitting a mirror and reflecting back. When it came into contact with the one-way mirror, it reflected into an eyepiece. In the path of this light ray, there was a spinning cog with teeth. Fizeau designed his experiment so that the cog was spinning, and he observed that the light passed through the gap between two of the teeth, reflected, and then he altered the speed of the cog so that the reflected ray passed through the next gap. He knew that there were 720 teeth on the cog, and that the cog was spinning at 25.2 rotations per second. So here we have the number of teeth that are passing by the light ray every second. And if we take the reciprocal of that number, then that is the time it takes for one gap to be replaced by the next. He altered the speed of the spinning cog until he got what he was looking for, and then, knowing that velocity is displacement divided by time, he calculated the velocity of the light. The light travelled twice the distance between the source and the mirror, and it travelled this distance. And it gave him a value that was only 4.5% higher than the speed of light. He did a similar experiment with the light moving through water, and he discovered that light moves more slowly through water. Later, in the 1860s and 1870s, Maxwell was doing his own calculations based upon the work of previous scientists. He studied the ideas of Faraday, and he developed Faraday's law. And he also came up with his own theory for electromagnetic waves. His theory was that electric fields and magnetic fields could oscillate together and be self-propagating through space. He calculated the velocity of these theoretical waves, and it was very close to the value that Fizeau had measured of light. So it was Maxwell's theory that light is an electromagnetic wave. And he calculated that the speed would be defined by two fixed values. the permeability of free space and the permittivity of free space. The permeability of free space is a property of magnetic fields, and it describes the difficulty with which a magnetic field penetrates a certain material. The permittivity of free space is a property of electric fields, and it describes how difficult it is for an electric field to penetrate a material. So it was Maxwell's theory that light is an electromagnetic wave, and it has a fixed velocity. At the time, it was thought that light requires a medium to travel through, and this was known as ether. Fizeau did further experiments into the flow of ether and how that affected the speed of light, but this was later proven not to exist. In 1879, in Germany, the Prussian Academy of Sciences issued a Berlin Prize, a challenge to scientists. They wanted to know if anybody could prove Maxwell's theories about light to be correct. At the time, Hertz was looking for a PhD project, and his supervisor, Helmholtz, tried to convince him to go for this prize. But Hertz thought that it was too much of a challenge. Several years later, he noticed while he was experimenting with some equipment that a spark on one side of a room generated a spark on the other side. And he designed an experiment to investigate this phenomenon. He set up an AC, an alternating current circuit, and he connected it to two arms. The spheres on each end acted like capacitors, and a spark was generated between the two electrodes. The arms were approximately 1 meter in length, and the globes were approximately 30 centimeters in diameter. The gap was approximately 7.5 millimeters wide. This was his transmitter. Several meters away on the other side of the room, he had his receiver. This was composed of two electrodes that were very close together, controlled with a micrometer, and a coil of wire. When a spark was initiated in the transmitter, a spark was observed in the receiver. But this was so small and so faint that Hertz had to have the room completely dark and allow his eyes to adjust, and he had to use a magnifying glass in order to see it. What was happening was that the transmitter was emitting radio waves, electromagnetic waves, consisting of an electric field and a magnetic field, oscillating at 90 degrees to each other, and they were going through the center of the ring. We know that if you have a coil of wire and a magnet moving upwards into that coil of wire, we know that it induces a current, and the direction of that current is predicted by Lenz's law. So what was happening here was that the magnetic field was creating this electric current and generating that spark. An electric field is also capable of inducing a voltage inside a conductor. Here we have the transmitter on the left side and the receiver on the right. If we make the transmitter electrons oscillate by putting a signal across the conductor, then we can create disturbances in the electric field. As those disturbances radiate out and come into contact with the receiver, then the electrons in the receiver are induced to move up and down as well. This creates a voltage in the receiver which can be measured. When Hertz changed the design of his receiver to two vertical metal bars, he still got a signal from the electric portion of his radio waves. And what happened was that they pushed the electrons to the top and then to the bottom and then back to the top of his metal bars, creating an oscillating signal. When he rotated his receiver so that it was no longer in the same plane as the electric field oscillations, he got no signal, indicating that the signal that he was receiving was polarized. He rotated his receiver back to the original orientation and got the signal, but if he put a polarizing filter in the way, that signal disappeared, further supporting evidence of polarization. He did further experiments and put a large reflector behind the transmitter. The waves that were generated backwards were reflected and strengthened the signal received at the receiver. After demonstrating reflection, he could also demonstrate refraction. He placed his receiver just at the right location and was able to see a spark. He set up his reflector in front and was able to create standing waves between the transmitter and the reflector, and he used his original design and placed it at different locations between the reflector and the transmitter, and was able to identify nodes and antinodes. And in doing so, he was able to measure the wavelength of the waves that he had generated. Because he had designed the equipment, he knew what the frequency of the transmitter was, which allowed him to calculate the velocity of the waves, which was very similar to the value that Fizeau had measured as the speed of light. It was known that light could reflect, that light could refract, and that light can be polarized. Maxwell predicted that light was composed of electromagnetic waves, with an electric and a magnetic component. The waves that Hertz had discovered became known as Hertzian waves. And he showed that they can be reflected, he showed that they can refract, and he showed that they can be polarized. And with his different designs of receiver, he showed that there was an electric and a magnetic component to these waves. He also showed that they travel at the speed of light. So Hertz had managed to prove that Maxwell's theories about light were correct. Light was an electromagnetic wave. And for a while, these new waves were known as Hertzian waves. When he was asked about the potential applications of his waves, Hertz replied, "Nothing, I guess." In 1892, a young Marconi heard about Hertz's research. Marconi investigated these waves and soon turned them into radio communications. Here is a plaque in London celebrating the first public transmission of Hertzian waves. and in 1910 they started becoming known as radio waves. In 1912, the Titanic set sail on its maiden voyage, equipped with the latest technology in radio communications. And when it hit an iceberg and sank, the radio operators were able to send distress signals which were picked up by nearby ships. And many people were rescued. At the inquest, it was said that those who have been saved through one man, Mr. Marconi and his marvellous invention. In 1935, a new unit was invented, the Hertz, replacing cycles per second.